You know, when you close your eyes and just picture a map, what do you actually see?
Oh, I mean, usually it's something hanging on a wall, right?
Yeah,
Or maybe a digital version on your phone.
right, exactly. But fundamentally, there's this expectation of stillness. Like a map is just a frozen snapshot of a place. The roads are where they are, the borders are totally fixed, and, the mountains obviously aren't moving.
Yeah, it's a single moment captured and just pinned down. And that snapshot is incredibly useful, but it's also well, a heavily curated version of reality, because reality refuses to sit still. Reality happens in 4 dimensions, not 2.
Which brings us to the core mission for today's deep dive. We are acting as your audio study guide to help you completely crush Section 207 of the GISP exam.
Yes, the GIS professional certification, that's a big one.
It is. And Section 207 is entirely focused on temporal data, which falls right under the geospatial data fundamentals category. Basically, we are taking that frozen snapshot of a map and we're hitting play. Because if you're going to pass this exam, you really need to understand how professionals move beyond just static geometry, right? You have to analyze trends, monitor events, model dynamic systems.
Absolutely. And the stakes here go way beyond just, memorizing vocabulary for a test.
Mm.
Whether you are dealing with environmental monitoring or urban planning or even emergency response, time is the dimension that makes spatial data truly actionable.
Yeah.
You are taking the X, Y, and Z coordinates of space and injecting the T coordinate of time. But before you can really analyze a timeline, you have to understand how a database actually structures and ingests that temporal information.
So let's start exactly there with the underlying data architecture. The baseline definition you really need to know for the exam is that temporal data represents a state at a specific moment or over a duration.
Right.
But looking at the specific formats they require you to know, the absolute most foundational one is the timestamp or the instant. It's just a single, discrete point in time tied to a feature.
A single moment, yeah.
And the documentation strongly emphasizes that this is often stored as an ISO 8601 string. So I have to ask, why does the exam care so much about that one specific string format?
Well, it's because standardizing date formats is just so crucial for cross-database querying, which is, what GIS professionals do all day long.
Oh, right, because of different regional formats.
Exactly. If you have a database field that just reads 01020223, a server in New York reads that as January 2nd, but a server in London reads it as February 1st.
Oh, wow, yeah, that's a huge problem.
It breaks everything. When you are running a temporal analysis across disparate datasets, that ambiguity just destroys your query. So ISO 8601 solves this by using a strict universal format. It's year, month, day, followed by hours, minutes, seconds. It completely removes the regional ambiguity, so the database knows the exact, precise instant an event, like a crime incident or a bridge inspection, actually occurred.
Okay, so the timestamp is basically the bedrock. But a lot of real-world phenomena don't just happen in a single second, and that introduces the concept of a time interval or a duration, which requires a defined start and a defined end.
Yeah, you need both bookends.
So if I'm visualizing this for the exam, a timestamp is basically like taking a Polaroid photograph, right?
Right.
Just a flash. But a time interval is more like recording a video clip with a distinct start and stop button.
That is a perfect analogy. And when you move from a Polaroid to a video clip, say mapping a construction project or a vegetation growing season, you are no longer just plotting points on a timeline.
Right.
You're dealing with temporal topology.
Mm-hmm.
The GIS actually has to understand how these durations interact with each other. Like, do two construction phases overlap?
Oh,
Or is there a gap in the timeline where literally no data was recorded? The database needs two distinct attribute fields to define the boundary on both sides of that event. That's what allows the software to query those overlaps and gaps alongside the space.
That makes total sense. Building on that complexity, the sources also talk about recurring time patterns. These are temporal cycles that just repeat, like weekly trash collection schedules or maybe seasonal flooding.
Yes, repeating cycles.
Okay.
Closely tied to that concept is temporal resolution.
Which is the update frequency, right?
Exactly. Temporal resolution dictates the granularity of your analysis. Like if you are tracking a really slow-moving demographic shift, a temporal resolution of 10 years, like the U.S. Census, is perfectly adequate.
Sure, you don't need daily census updates.
Right. But if you are tracking a live wildfire, a 10-year resolution is completely useless. You need an hourly or even minute-by-minute resolution. The exam really tests your understanding of how to match the temporal resolution to the actual phenomenon you are trying to map.
And that distinction naturally leads us into the difference between historical data and real-time data. Historical data is archival, so looking backward at, say, land use changes from 1990 to 2020.
Archival static data.
Right. But real-time or near real-time data is live. And when we talk about live data in a professional GIS setting, we're usually talking about feeds from an API or IoT Internet of Things sensor data, like a stress sensor on a bridge sending continuous telemetry back to the server.
And you have to consider the massive processing power required for that. I mean, historical data just sits quietly in your database waiting to be queried.
It's just hanging out.
Yeah. But real-time data from an API, that requires the GIS to continuously ingest, parse, and render new information constantly on the fly. It's a completely different architectural demand.
Wow.
But then you also have this hybrid approach, which is version time. Sometimes they call it temporal snapshots.
I really want to dig into versioned time because this feels like a crucial concept for the exam. It's described as capturing distinct versions of an entire dataset at specific times, like tracking how city zoning revisions evolve over decades. It sounds like you are essentially saving alternate universes of a city's layout.
Alternate universes is honestly the best way to frame it. Think about a city planner who needs to see the zoning map exactly as it existed on, say, May 4th, 2015, right before some massive rezoning ordinance took effect.
Okay, so they need to go back in time.
Exactly. Version time doesn't just track when a single building was built. It preserves the entire state of the relational database at that exact moment. You could roll the entire system back to that alternate universe, run your spatial analysis on the historical state, and then roll it right back forward to the present day.
Okay, so the database is capturing these states, whether they are instance, intervals, or massive version snapshots. But how does the system actually handle the rhythm of this data coming in? Because time isn't always neat and orderly.
Oh, definitely not.
The sources say data collection typically happens in two ways, at regular intervals or at irregular intervals. Regular intervals make perfect sense to me. A water monitoring station logging stream flow data exactly every 15 minutes, without fail. The database expects it.
Yeah, the structure is highly predictable. The database is literally just appending a new row every 15 minutes.
But irregular intervals are where data is recorded only when an event actually happens. So lightning strikes, earthquakes, traffic accidents. From a database perspective, isn't irregular data much harder or more chaotic to manage?
It seems like it would be.
Right. I feel like querying a system where you have no idea when the next data point is coming would be incredibly inefficient compared to a nice, neat 15-minute log.
It's a really common assumption that irregular data breaks the system, but spatial databases are specifically engineered for this. They use spatial temporal indexing.
Spatial temporal indexing. Okay.
Yeah. When a lightning strike occurs, it gets logged. To find that event later, the database doesn't scan every single row of time since the dawn of creation. Instead, the index allows the query to draw a bounding box in space, say a specific county, and a bounding box in time, like between 2 p.m. and 4 p.m. on Tuesday.
Oh, wow. So a bounding box for time.
Exactly. The irregular nature of the data doesn't slow down the database at all. It just changes how the GIS renders the gaps. If there are no lightning strikes for 3 days, the visualization simply remains empty until the temporal index hits the next logged event.
That makes a lot of sense. The bounding box applies to the time dimension just as much as the spatial dimension.
Okay.
So we established earlier that a single moment, like that lightning strike, gets one attribute field for its timestamp.
Yep.
And a duration, like a fire perimeter burning over several days, requires two fields, a start date and an end date.
2 fields, yes.
But what do you do with a layer that doesn't have any time fields built into its attribute table at all? Are you just completely unable to use it in a temporal analysis?
No, you are definitely not out of luck, and this is a really critical workaround to know for the GISP exam. You can take a non-temporal layer and make it time-aware manually.
How does that work?
You do it by applying a fixed time extent and the layer properties. Let's say you have a highly detailed drone orthomosaic of a construction site. The image file itself might not have a database table with a start and end time for every single pixel.
Right, it's just a flat image.
But the flight happened on January 1st, and that terrain was completely excavated and changed by March 31st.
Oh. So you essentially put an expiration date on it, like a carton of milk.
Exactly like a carton of milk.
You go into the layer properties and tell the software, treat this entire static image as perfectly valid and fresh from January 1st to March 31st. As long as the user is viewing the map within that temporal window, the image renders.
Yes.
But the moment the timeline hits April 1st, the expiration date hits and the image instantly drops off the map.
That is the exact mechanism. You are forcing static geometry to obey dynamic temporal rules, which honestly transitions us perfectly into the user interface side of things.
Right, because everything we just talked about is the back end.
Exactly. Storing the data correctly, setting up your ISO 8601 strings, your double fields for durations, your fixed extents, that is all back-end database administration. But the exam also tests your mastery of the front-end tools, the tools GIS professionals use to actually manipulate that data on the screen.
So let's talk about visualizing those time-aware layers. The exam outline points to 3 distinct map types you really need to differentiate. First is the static map.
Which is just one single period of time, the classic frozen snapshot we talked about.
Right. Second is the dynamic map. This is a single interface allowing a user to slide back and forth between time periods to watch changes happen in place. And third is the multiple maps approach, where you place several static maps side by side in a layout to visually compare different eras simultaneously.
Spot on. And for that dynamic map, the core engine driving the visualization is the time slider.
The time slider.
Yeah, it's the primary tool in the interface for exploring and filtering temporal data. But there is a massive operational detail here that frequently appears on the exam.
What's the detail?
The time slider doesn't just change the visual geometry on the map. Table views that are open for a time-aware layer will automatically filter their displayed rows based on the map's current time extent.
Wait, really? So the map and the underlying spreadsheet are intrinsically synced
Yes.
automatically?
So if I drag the slider to show only crimes that happened in October 2022, my attribute table instantly hides every single row of data from September or November.
Instantly. You aren't just filtering pixels. You're filtering the relational database query in real time. You are filtering the selection tools and the geoprocessing environment, all of it.
That is incredibly powerful.
It is. Now, you can disable this automatic filtering in the table settings if you need to, like perform calculations on the whole dataset while only viewing a sliver of it on the map. But by default, that temporal filter is universal, which I imagine introduces a major challenge when you start bringing in multiple datasets from entirely different sources. Like, if I'm building a dashboard for an emergency operations center, I might be pulling in a live weather API that runs on UTC-coordinated universal time.
Right.
But my local ambulance dispatch data is logging events in Eastern Standard Time. If I just turn on the time slider, that UTC data is going to be visually offset by 5 hours from my local data, isn't it?
It absolutely will be. And this is exactly where the concept of map time becomes critical.
Map time.
Yeah. A map, as a container, can actually be made time-aware, independent of the layers inside it. Defining map time forces all the temporal values in your configured layers to align to a common time zone.
Well, that's clever.
The software does all the complex math in the background, converting the UTC weather feed and the EST dispatch feed into one single unified temporal framework.
I love that. I visualize map time as sort of like the conductor in an orchestra.
Oh, I like that.
Yeah, you have all these disparate data layers playing their own instruments, operating on their own native time zones. And if you just let them play, it's temporal chaos. But the map time conductor steps up to the podium and basically forces every single layer to play to the exact same temporal beat.
That's exactly what it does.
It guarantees the user isn't accidentally comparing a 2 p.m. weather event to a 7 p.m. traffic accident just because the database servers were located in different time zones.
It is the ultimate synchronization tool. And that synchronization cascades down through the entire project. The time zone adjustment imposed by the map time conductor affects the attribute table, the pop-ups when you click a feature, the legends, and even the printed layouts.
Everything follows the conductor.
Everything. But for the conductor to actually do their job, the underlying data must be properly formatted. The exam really emphasizes this. Temporal data must include a field containing the recorded time, stored as either a proper date string or a numeric field.
So no casual text entries.
Exactly. If you just type Tuesday afternoon into a text field, the conductor can't read the score, and the layers simply won't sync.
Good to know. Okay, beyond the time slider and map time, there are 2 more front-end tools we really need to lock in for the exam. Bookmarks and animations. Traditionally, I think of a bookmark in GIS as just saving your spatial extent, right?
Right, like bookmarking a specific intersection so you don't have to manually pan and zoom back to it.
Exactly. But when working with temporal data, time properties are also baked into that bookmark.
They are. You are capturing an exact intersection of space and time.
Okay.
If you bookmark the eye of a hurricane at 4:30 p.m. on a Thursday, clicking that bookmark later doesn't just snap the camera back to that geographic coordinate. It snaps the time slider back to 4:00 p.m. Thursday, instantly restoring the exact analytical state you were viewing.
That's so useful.
And if you string a series of those states together, you get an animation.
Which is huge for presentations. Animations allow you to export the progression of your time-aware layers into a standard video file, which really solves a major communication problem.
Oh, a massive one.
You can build the most sophisticated temporal analysis in the world, but if you hand a complex GIS project file to, say, a city council member who doesn't know how to use the software, the analysis is totally useless.
Completely useless. But exporting an animation translates that complex database query into a format anyone can understand. It bridges the gap between technical analysis and stakeholder communication.
Definitely. Okay, so now that we understand the database architecture and the visualization tools, let's look at how the GIS exam actually tests your ability to synthesize all this information. Because the exam doesn't just ask for definitions, it asks for real-world applications.
Right. They want to know you can use this stuff.
The curriculum highlights several specific real-world scenarios. It mentions tracking the historical land use patterns of Hong Kong in 1990, mapping the total rainfall in Honolulu on July 1st, 2009, monitoring population increases per city, and viewing global ocean temperature changes.
And notice how those examples test totally different facets of the temporal data we've discussed.
Oh, yeah.
Like, the Hong Kong example uses historical version time to model urban sprawl. The Honolulu rainfall is a specific time interval, a 24-hour duration. And the ocean temperatures require analyzing regular intervals over a massive spatial scale.
Which leads us perfectly into the official sample question provided for Section 207. Let's break down the logic of how the exam writers formulate these questions. Are you ready?
Let's do it.
The prompt asks, which of the following statements accurately describes the applications of temporal data in GIS? We have 4 options to evaluate. Option A. Visualize the locations of ocean mammals to understand patterns in their movement. Option B. Understand population increases per city. Option C. Indicate how fatalities from a disease are increasing based on changing colors in the layer symbology. Or option D. View ocean temperature changes or weather patterns over time.
And the answer key states all of the above.
All of the above. Now, options A, B, and D are pretty straightforward. They represent the classic tracking of movement, growth, and environmental change. But I really want to dive deep into option C because it highlights a very specific advanced technique.
Changing colors.
Yes. Indicate how fatalities from a disease are increasing based on changing colors in the layer symbology.
Hold on. So we aren't moving a geometry across the map and we aren't adding new polygons. We are just changing the color of a static point based on time, and that counts as temporal data visualization.
It absolutely does, and it is a brilliant example of avoiding cognitive overload in map design.
How so? Well, think about it. If you have a hospital location and you want to show fatalities rising over a 6-month period, rendering a new map point for every single fatality would quickly turn the map into an unreadable mess of overlapping dots.
Oh, right. Just a giant blob of points.
Exactly. So instead, you tie the time slider to the dynamic symbology engine. As the temporal index moves forward, the software reads the rising fatality count in the attribute table and pushes the static hospital marker along a color ramp.
Ah, like scaling from pale yellow to dark crimson.
Precisely. The geometry remains perfectly static, but the attribute data drives the visual severity. It allows the viewer to instantly grasp the changing state of the situation without having to click on the point and read the underlying database row.
The color itself becomes the temporal indicator.
Yes, it proves that temporal data isn't just about showing where things go, it's about showing how things evolve in place. Whether you are tracking a migrating whale across the ocean, watching a stationary city's population swell, or observing a localized outbreak intensify through a shifting color ramp, time is the indispensable variable.
That is just incredible. And really, that is the core takeaway for Section 207 of the GIS pre-exam. To pass this section, you need to remember that time requires specific data fields. You need to know that a timestamp requires a specific string format like ISO 8601 to function across systems, while a time interval requires 2 distinct fields to establish that temporal topology.
2 fields, yes.
And you need to understand that irregular event data isn't chaos. It's smoothly managed through spatial temporal indexing. Plus, you must know how to use the time slider to filter your relational database while relying on the map time conductor to synchronize competing time zones into one unified analysis.
Mastering all these mechanics really represents a fundamental evolution in how you approach geospatial problem solving. But, it also introduces a massive theoretical shift.
What do you mean?
Well, if temporal data allows us to perfectly model the past, through version snapshots, and monitor the present through real-time API feeds and dynamic symbology. At what point does GIS stop being merely a record of what has happened and become a predictive engine for modeling exactly what will happen next?
Wow. From a frozen snapshot on the wall to a dynamic dashboard to basically a predictive crystal ball.
Exactly.
That is an incredible trajectory to consider. Well, you now have the architectural logic and the practical applications locked in. We enthusiastically wish you the absolute best of luck on Section 207 of your GISP exam. Go crush it.